The Newton-Raphson algorithm extends to any number of simultaneous nonlinear equations. At each step, linearize the full residual vector through the Jacobian matrix and solve a linear system for the update. 2 iterations usually achieve machine precision. The cost per step is 1 Jacobian evaluation plus 1 linear solve, typically negligible for small engineering systems. The algorithm has 5 steps that repeat until the residual norm falls below tolerance. Step 1 sets the initial guess x0. Step 2 evaluates the residual vector f and the Jacobian j at the current iterate. Step 3 solves the square linear system, j delta x equals minus f. Step 4 adds the step delta x to the current iterate. Step 5 checks whether the residual or step norm is small enough. If yes, stop. If no, return to step 2 with the new iterate. For the two-stage turbine, differentiate each equation with respect to each unknown. The partial of F1 with respect to T1 is 1 plus T2. The partial with respect to T2 is T21. By symmetry, the second row gives T2 and 1 plus T1. The Jacobian is state dependent. It changes at every iteration because the derivatives involve the current values of T1 and T2. At the initial guess T1 equals 10 and T2 equals 5, the residual vector is minus 10 and minus 5 with norm 11.18. Plug into the 2 by 2 Jacobian entries 6, 10, 5, 11, determinant 16. Solve by Cramer's rule. Delta T1 equals 3.75. Delta T2 equals minus 1.25. Add to get T1 equals 13.75. T2 equals 3.75. The Python function takes f, j, and an initial guess x0 as arguments. It loops up to 50 times, calling NumPy linear algebra solve to compute delta x each iteration. As soon as the step norm drops below tolerance, it returns the solution and the iteration count. Define f and j as lambda functions using NumPy arrays. Pass both to Newton_Raphson along with the initial guess as a NumPy array. The function returns the solution vector and the number of iterations, here 5. 4 rows capture the full convergence history. At step 0, the residual norm is 11.18. The first Newton step cuts it to 6.63. The second step brings it to 0.09, already small but not yet at machine precision. The third step finishes it, T1 equals 14, D2 equals 4, residual 0. 3 steps to machine precision zeros. Quadratic convergence is visible in the residual sequence 11, 6.6, 0.09, 0. Each drop is the square of the previous one. EES solves the same two equations with its own Newton-Raphson and numerical Jacobian. Writing the equations implicitly gives T1 equals 14 and T2 equals 4, matching the Python output exactly. The Jacobian block shows the analytical entries at the solution for comparison. Newton-Raphson for nonlinear systems. Week 1.